What is a moment? Very, very tricky question. What is a moment? You find that after, when you become a practicing engineer, you will be dropping this word moment every now and then, but when someone asks you what is a moment, you're kind of paralyzed because it's difficult to define a moment. Moment is always discussed in terms of moment of a force. What is the moment of a force? I'll give you the answer. Moment of a force is a product of the force and its distance from an axis perpendicular to the plane containing the line of action of the force. The effect of the moment is to cause a rotation about that axis. The effect of force is to cause translation. Effect of a moment is to cause rotation. F equal to ma has to be now changed to m, capital M is equal to I a double dot or omega dot. So, simple example, let's take a wrench like this and you apply a force F. You're actually applying a moment. You're trying to turn a nut with the spanner, so the nut is subject to a moment M equal to Fd. We all know this. This lady is trying to pull that door open, so the door is opening, its axis of rotation is vertical in that case. We've all done this when we were kids. I hope you're still doing it in the park. Swinging up and down, the axis of rotation is, in this case, horizontal. So whenever you talk of moment and rotation, you must be clear what is the axis about which the moment is applied, what is the axis about which the rotation takes place. Then only you can define a moment. So if you talk of a load, we use a word called external moment. Now you'll be doing problems later where that you'll be shown pictures like this and you'll be also giving answers, but you should ask a question. How do you apply such a moment? So you must always relate theory with practice. How do you apply this moment? Well, that's where the concept of couple comes. You can't apply moment so easily, so invariably you are applying two parallel forces, equal and opposite, separated by a distance. For example, if you do this, you'll get the same effect. Let me say I have a rigid vertical bar connected to this and I apply a force P on top, force P below on that bar, and this forces this bar beam AC to turn, and the distance of separation is A. So I have three bodies there, the beam A, which is body A, and the vertical bar, the top half is body B, the bottom half is body C. If I separate out the free bodies, now you know what a free body is, the bodies B and C will look like that. To balance this P, I have to put a force P here, but still it's going to rotate. I have to put some other symbol. This curved arrow is what we call a moment. M is equal to PA2, and similarly I have to do that here. But this whatever I get here by Newton's third law gets transmitted to the beam AC. So this green arrow and this purple arrow and what you get here should be passed on by Newton's third law to the beam. The purple arrows cancel out because they are equal and opposite, but the curved arrows will sum up. They are both acting anti-clockwise, and that's how I get the equal and opposite thing is clockwise. That's how I get P. That's the story. PA is M. So I might show you only this, but the hidden story behind all this is this, and I can separate this distance as much as I want. The more I separate, the less force I have to apply. That's the lever principle. Okay. And the curved shape will look like this. This part will sag, this part will hog, this will go down, this will go up. Remember, a moment acting as a load on a beam causes bending, and internal forces, which we'll see shortly, is bending moment and shear force. But a force can also cause the same thing. So we treat both as external loads. It could be a force, it could be a moment. both will cause bending. But often mechanical engineers think of bending in terms of shafts rotating and so on. So you should also know that this is also a moment, okay, but this causes twisting, not bending. You must know the difference. It's outside the scope of a topic, but you should also know that that's also moment, but this is rotation about a longitudinal axis. This is called twisting, and the external moment that you apply, the word is torque. You apply a torque, and you'll find that if you are rotating a cylinder, the circles remain circles. That's the principle of torsion, whereas the longitudinal lines will take a helical shape. Okay, so this is outside our topic, but since we touched moment, we should also touch twisting moment. We are now going to the fourth topic, support reactions. Equilibrium, we've studied this, so I'll do it quickly. The condition of static equilibrium, which you can derive from Newton's first law of motion, says unless you have an externally impressed force, there will be no acceleration. A body will remain in a state of rest or uniform motion unless there is a non-zero resultant force or moment acting on it. He said force in his original derivation, but now we say, you can also say moment. Force will cause translation, moment will cause rotation. In a beam, a force will also cause slope and deflection, and a moment will also cause slopes and deflection. So these are vectors, and in a three-dimensional space, the resultant force F must be 0. So you say Fx, this is dot I, this is a unit vector, Fy dot j, Fz dot k. So and similarly, moment, you can talk of Mx dot I. You have to sum up all the moments. Actually, you have 6 scalar equations of equilibrium, but easily you can write them as 2 vector equations. And most of our structures are planar structures, at least in the beginning we learned that. So if you talk of only one plane, then these 6 equations reduce to 3 equations, sigma fx equal to 0, sigma fy equal to 0, and sigma mz about any axis normal to the plane equal to 0. The definition of a planar structure is that all the parts of the structure, like a plane frame, lie within one plane, but in addition the loads also act on that same plane. It will not be possible to generate more than 3 linearly independent equations of static equilibrium in a planar structure and 6 equations in the general case of a space structure. Please note, sigma, if you take any body in equilibrium and you define your x-axis and y-axis and z-axis, then sigma fx equals 0 will give one unique equation. Sigma fy equals 0 will give another unique equation. But sigma m about any z-axis equals 0, you can write 100 equations, 1000 equations. So you can choose a point about which you are applying the moment. But it doesn't mean you will get actually 1000 equations. Please note, whatever you do, you will get only 3 independent equations of equilibrium. You need not even write sigma fy equals 0. You can write of this 2 moment equation. So in terms of rank, you should understand that the matrix is limited and it has a rank, and if you write additional equations, they can be reduced to the same old 3 independent equations. Okay. Now let's talk of support reaction. I put a boulder there, but it could be a beam, it could be a truss, it could be an arch, it could be anything. So I've got a heavy weight, or let's ignore the self weight of this. Let's put a concentrated load W acting somewhere here at a distance A from the left support and B from the right support. The support conditions are classic, simply supported conditions. Tell me, what is the reaction at A and B? By the way, what reactions you get? You can get, because this is restrained from moving to the left or right, you can potentially develop a horizontal reaction. This is restrained from going down, you'll get a vertical reaction. So there are 3 unknown and you have 3 equations of equilibrium. So you should be able to get them. One of these equations is obvious. If you apply the first equation, sigma f x equals 0, you know that HA is going to be 0, right? That you know, everybody knows. Now, let's not apply any equation. Let's do it intuitively. Let's move this W slowly from A to B. If W is at A, if I put the load here, what will be the reaction VA? It will be W. What will be the reaction VB? It will be 0. Now, let me shift the load W in exactly in the middle of AB. How much of W will go here? How much of W will go there? Half and half. Common sense. Intuition. You don't need equation. You don't need calculation. What happens if you shift W all the way to the end B? The entire load will go to the support reaction B. Nothing will come there. So, in general, the closer W is to the support A, it will generate a higher reaction here and a lower reaction here, and the sum of the reactions must be equal to W. So if you say the y-axis is positive, this is how you write VA plus VB minus W equal to 0, which is like saying VA plus VB equal to W. Now, you can guess the answers, but let's prove it mathematically. You can take moments about any axis. Usually, you should take moments about an axis which passes through one of the unknowns. So, if you take moments about the axis passing through A, the z-axis passing through A, then you will find that VB gives you an anti-clockwise moment, VB into L, so you put minus VB into L, and W gives you a clockwise moment with respect to A, which is W into A. You're just doing the lever principle, and so you can prove from this equation. You could write this equation first, VB is WA by L. Now you wrote something mathematically, understand it physically. A by L is a ratio. So it's a very important lesson. That fraction of W will be transmitted as a reaction to A, which is given by the ratio A by L. If A is 0, VB transmitted to B, VB will be 0. If A is L, it will be 1. And similarly, if you plug in here that fraction, so W will transmit some part to A and some part to B. The part it passes on to A is B by L times W. The part it passes on to B is A by L. Never forget this. You don't need equation. You got the intuition, you'll do it. And so that's the solution. Let's try to, now you can also take moments about B and prove the same thing. That doesn't matter. You have only 3 equations, answers are unique, you can't get a different answer. Let's try to draw a graph of the support reaction on the y-axis and the distance A by L on the x-axis. We're now putting what we discussed first. When you have the position of the load at A, you will find that the green line VA will be W and VB will be 0. So if you put the units, VB will be 0. If you shift to this side, VA will be 0 and VB will be 0. So this is a fraction of the load, very easy to answer. If you put the load exactly in the middle, half-half. Got it? Very easy. Now let's make it a little complicated. By the way, this problem, beam with overhang, is a standard question we ask students when they come for admission for MS and MTech, and this is the one question they are not able to answer. What happens when you have a beam with an overhang? So pay attention. It's very nice and simple. So we have a beam with overhang. I'm putting a load 20 kilonewton here, okay, and I'm going to put this dimension as A. Tell me what happened to VA and VB as I move this. Well, if the load is somewhere here, it's going to deflect like this, and this region will remain straight. Why will it remain straight? Because if I take a free body here, if I cut a section here, there's no load, there's no reaction, so there's no bending. This will remain straight. The overhang will remain straight, except when I put the load on the overhang. Note that. If the load is here, then what I can do in my mind is, if I want to find VA and VB and I restrict A to this, I can throw away BC in my mind, make it simple, and I can draw the same thing. Is it clear? As long as this load does not encroach into the overhang, the answer is very clear. 20 kilonewton in the middle will give 10 here, otherwise it will be 20 here, 0 here, 20 here, 0 here. So the same picture. Now what happens if I put the load into the overhang? Listen carefully. What happens? Let me begin by putting the load at the free end C. What will happen? Tell me what is VA? What is VB? And this is tricky. Normally if I apply a load and there are two reactions, the reactions will be less than the load. But I have a funny case here where that normal rule is violated. How to do this? Anybody? What will be VA? Well, you can just blindly do it mechanically, applying the equation. So this is a deflected shape. AB is going to hog, BC is also going to hog. Equilibrium equation, sigma Fy equal to 0. Sigma Fx equals 0 is not worth putting here because there's no, we know HA is 0. Two equations, plug them in. Okay. I hope you know how to do that. Solve them. You will find VB is 25. You put only 20 kilonewton, you're getting a reaction higher. Why do you get higher? Why do you get a higher reaction? You get a higher reaction because you remember that counterweight we discussed earlier, because the beam wants to lift up from the left support A. It wants to lift up and you have to hold it down. And that's what the reaction VA is holding it down. It's actually pulling it down by 5 kilonewton downwards. So that 5 kilonewton is downward. The load 20 kilonewton is downward. For equilibrium, something upward 20 plus 5 should act, and that's going to act at B. That's the reason why this is happening. And so what happens is the VB line simply proceeds and now exceeds from 20 to 25, and similarly VA goes to the negative side to minus 5. Very interesting when you draw a graph. So it's all linear. The relationships are linear. Sometimes it's positive, sometimes it's negative, and you can learn something more when you separate out the two beams. When you separate out the two beams, you can always separate out. In life, everything is complicated. That's why we call those big systems, systems. You have a structural system, you have a political system, you have an economic system, you have a physiological system, very complicated. To understand any part, you have to separate the part from the system. It's called a subsystem. But when you separate and look at the subsystem, you must know also the connection of that subsystem to the larger picture. Here, we have separated ABC into two pieces, AB and BC. AB we can draw as simply supported, but BC, we have a problem because the support at C it's free end, at B we have to put the right support. At B it cannot translate, cannot go down, cannot move to the left or right, so a hinge support is correct. But it cannot freely rotate. The beam AB is giving some continuity at B, remember. So the right support to put here is a rotational spring support. If you want to know what is that rotational spring stiffness, like a door closer, if you pull more moment, it will move faster. If you put less, it will be slower. So this rotational spring has a stiffness in terms of kilonewton meter per unit angle of rotation. You can find that out, but that's not an issue. I just want you to correctly show this. And now if you apply a load 20 kilonewton, it's going to behave like a cantilever. You will have a reaction here and a moment there. This reaction is 20 kilonewton. This moment is going to be 20 into 0.5, 10 kilonewton meter. That's a moment. This, by Newton's third law, gets transmitted to AB. This doesn't get transmitted, it goes straight to the support, and so your problem has now reduced to a problem AB subject to a concentrated moment 10 kilonewton meter, which needs 5 kilonewton meter acting upward at B and 5 downward at B. You join 5 and 20, you get 25. So you've learned so much from this. So there are many ways of learning, and you can also draw the deflected shape. Example, one more example. Okay, we've done this before. Remember? Parent, child, we've done this, we know the answers. You can do it the hard way by writing equations of equilibrium. You can do the quick way. You have three. This is a little tricky. Why is it a little tricky? Well, strictly you should put a horizontal reaction here also, but that is 0. So you've got three equations of equilibrium, three unknowns VA, VB and MA, but you have only effectively two equations of equilibrium, sigma Fy equals 0, sigma M equals 0. So this looks like it's statically indeterminate, two equations of equilibrium, three unknowns. How do you solve this? Well, you got an internal hinge there. That hinge will giving you an additional equation of equilibrium. Two bending moments later, it's saying that the bending moment at C is 0, but right now we will just look at it from a separation point of view. I'll separate out AC, I'll separate out BC, and I can show the parent-child behavior which I discussed earlier. Now look at the child. The child has a 20 kilonewton load acting bang in the middle. So what will be the reactions? We all know that the reactions are 20 will be shared equally here, 10, 10. Got it? And there is not going to be any moment here because of the hinge. Moment will not transmit any, the hinge will not transmit any moment across the hinge. So Newton's third law, 10 will come here as a load. Got it? This is a cantilever. So common sense tells me that I must get a reaction here 10 and I must get a moment here 10 into 4 acting anti-clockwise 40. Finished. I've got all the answers. This is a very clever way of doing it, but I think in your exam you can do this, but they will like to see nice equations. So you can do it the hard way, separate them out, write the equations. Okay. But good engineers do it much faster on the free body itself. You got the answers. Very interesting problem. Let's take one or two more. This is not really a beam, but since we are on the topic action, this is a cantilever space frame. Okay, look at this. I've got three axes. X axis is aligned along the shaft. Y axis is vertical. Z axis is along this part of the cantilever. Please note, whenever you draw axes like this in Cartesian space, you have to satisfy the vector rules I cross j is equal to k, right? So x pointing this way, y pointing this way, right hand corkscrew rule, z has to point this way. So just by the way, you should not put z the other way. Now how do you find first of all, what are the reactions? How many reactions will you get at A? How many reactions? Can you do it yourself? Okay, I'll tell you that you can draw the reactions like this. You've got three axes. Okay, double arrow shows a force, a double arrow vectorially shows a moment, right? So in the x section, I'll say the force is Rax, the moment is Max. This is horizontal. In the z direction, which is also horizontal perpendicular, I have Raz and Maz, and in the vertical y direction, I have Ray and May. Ray is not written here, right? 6 unknowns. We are just finding support reactions by applying equation of equilibrium. There are other ways to find support reactions. You can use principle of virtual work, and we are not doing all that. Okay, someone's given an answer. I'll help you. Equilibrium equations are these. You know them. Just apply them. Rax, Ray, Raz with the directions here. If you give me plus or minus, the units of Rax, Ray and Raz should be kilonewton. The units of Max, May and Maz should be kilonewton meter. Okay, you try. Rax plus 30 equal to 0, very easy. See, in the x direction, you have 3 loads here. This is pointing in the x direction. Your reaction Rax is also here. Sigma Fx equals came where? Which college? Yeah. Someone's given all the answers. Brilliant. GCT Coimbatore. Great. Minus 30 plus 20 plus 10, 120, 90, 60. Another one. There is, see, here itself 2 answers are contradicting one another. So you get unique answers. Okay, let's see. At least you're giving answers. I'm happy. Right or wrong is, we'll see. Come. So check out whether you got this right. Rax plus 30 equals 0. So Rax is minus 30. Full marks. Ray minus 20 is 0 because Ray is pointing, Ray is up and 20 is pointing downward y direction. So Ray is plus 20. Raz minus 10 equals 0. How much time do you need for this? Very simple. Moment also. Take Max. This is right hand corkscrew rule. You will find that this 20 kilonewton meter force will have a moment of 3 meter. Lever arm is this. It's going to rotate about the x axis, which is aligned in this direction, right? So minus 60. Similarly, you can solve this. Okay, please do this. These are the answers. Figure it out. Very easy. For beginners, you should get 100% in such problems because very simple. Just stick with it. Now is a tricky problem. Remember I showed you this, one day you will be designing bridges like this. At least now you should know how to get reaction. So we will make it simple. We'll put the 2 internal hinges and we apply the load P here. How many support reactions? Okay, so I'll also make it easy for you. How to solve this? Parent child makes our job very easy. So common sense. This P is acting there. So it will give reaction. If it's in the middle, reaction of P by 2, P by 2. Newton's third law, P by 2 goes as loads on the parent simultaneously. Now finish it. Score the goal. What is the reaction at A, B? This is a beam with overhang problem. Very easy. What is RA? What is the reaction at A and B? At least give me the reaction at B. We've done this before, you should be able to crack it. See, this original problem looks scary. But when you separate out into parts, it's very simple. That's how life is. Everything is simple if you understand what's going on. So, if you want to do it mathematically, you will find VA is P by 4 and VB is 3P by 4. See, always when you get pictures like this, note that this reaction will be more than this reaction. Why? Because it's sitting on an overhang. Now, how much more? You can work it out, solve this equation, and this there will be an uplift here. So the direction is important, which means in detailing, when you actually make sure this doesn't ever lift up. Normally we put rubber bearings, it will lift up. So you have to have a bearing which holds it down. Very important. Okay. So whatever you get symmetrically, you will get that. These are your answers. Right. This is a challenge for you. Please do this problem. Now I made it a little complicated. The complication is I've got not the standard simple support. Someone turned the roller around like this at 45 degrees to the horizontal and vertical, and to make matters worse, the load is also inclined at a ratio, the horizontal 3:4. Obviously, this to make calculations easy, because if this is 3, this is 4, Pythagoras rule says this is 5. You can give theta, but theta and all is not needed. This is all that you need. Question is very simple. First of all, what are your reactions? If you stick to Cartesian coordinates, you have HA, VA. HA is horizontal at A, VA is vertical at A, and you have HB, VB. Here's the clue already leaked out to you. The one thing you know for sure, that because the roller is at 45°, they are not independent. These two guys are related to each other because the resultant reaction must be normal, because this is rolling here, it cannot have a restraint, must be normal to this plane RB, and if you resolve VB and HB, it will point in this direction. The question is to find RB, but it's nice to talk of VB and HB equal. So it's not a difficult problem. You've got three unknowns because now you treat only as RB. Three unknowns, three equations, sigma fx equals 0, sigma fy equals 0, and sigma m about any axis equals 0. To make life easier, that load 30 kilonewton also you can resolve into vertical and horizontal components. So if you use trigonometric ratios, 3 divided by 5 of 30 kilonewton will be the horizontal component, that's 18 kilonewton. 4 divided by 5, the vertical component of 30 is 24. That's the easiest way to do it. Good examiners don't want you to press the calculator too much. They want to use your brain. So they'll give you tests in which you don't need any calculator. That's how this problem is chosen. So you can resolve that load into a vertical component and horizontal component whose values you know. Now your life has become easier. Wait. Firstly, this horizontal reaction 18 is going to be shared by HA and HB in some proportion. Okay, don't worry about it. This is not going to affect your vertical reaction. This vertical 24 kilonewton, how much of it will go to A and how much will go to VB? Can you tell me? How much of this 24 kilonewton will go to VA? Remember A by L, B by L logic. So B by L, 6 by 9, which is 2/3 of 24 kilonewton will come here, and the balance will go here. This will be heavier than this. That's how you do it quickly. 2/3 of 24 is 16, 1/3 of 24 is 8. Finito. If this is 8, look at the thinking, then this must be also 8. If this is 8 and the horizontal component is 18, the balance must be taken by this. Oh, huh? No, this is a tricky problem because it's not a balance. Both are pointing in the same direction. So 8 plus 18 must be taken and it will point the other way, 26. Very interesting. So you see, you get equilibrium satisfied. You can do it straight on this, but to get marks from your teacher, it's good to write the actual equation. But as engineer, you should do this first. Write the equations so that teacher will not suspect you copied from somewhere. Write it all down the big way. Sigma fx equals 0, sigma fy equals 0, sigma m equal to 0. 16, 8. Very good, very good. Any more answers? Someone gave 32. See, now you have the confidence you can find support reactions in any problem if it's statically determinate. See, whatever we did that, you can write down in long form, and your resultant force is a resultant of this, which is square root of 8 and 8, which is 8 root 2, 11.3. If at all you need a calculator, it's here. But even if you write 8 root 2, you'll get full marks.